Section 11.8, we talk about a power series. So let's start with the definition of this type of a series. So a power series is a series of this following form. So it's a summation as n goes from 0 to infinity of c sub n times x to the power of n. So that means we just start with c naught, our very first, and all the c's here represent coefficients. So this is our very first coefficient, times x to the 0, which would just give us 1, plus c sub 1 times x to the first power, plus c sub 2 times x squared, and so on. Where x is a variable, and c sub n are the coefficients of the series. So really this is a polynomial of infinite degrees. It just goes on. Now for a fixed x, this is a series of constants that can be tested for convergence or divergence. It all depends on what value we substitute in for x. Now the sum of the series we'll write this as a function here. So the sum of the series f of x is equal to summation n goes from 0 to infinity of c sub n times x to the nth power is a function whose domain is the set of all x for which the series converges. So we'll take a look at an example. Let's say we have a summation as n goes from 0 to infinity of just x to the nth power. So we'll start to write this out. So x to the 0 is just 1, then we'll get plus x to the first, plus x squared, plus x cubed, and so on. And hopefully you recognize this. If we were to kind of go back and just look at the sigma notation here, that this is a geometric series. Where a is equal to 1, r is equal to x. So this series converges to that sum. Remember the sum of a geometric series is a over 1 minus r, so that becomes 1 over 1 minus x if the absolute value of x is less than 1. So our next definition now, we're going to take a look at what we call a general power series. And this is a series of the following form. The summation as n goes from 0 to infinity of c sub n times the quantity x minus a to the nth power. So this is still a power series. In x minus a, or how we refer to this, a power series centered at a. If x is equal to a, then this is convergent with the sum of c naught, our initial c value. Now, to determine where a power series converges, we can use the ratio test. So that's what's nice about this section. We're going to get more practice with using the ratio test. Now, before we get into some examples, I want to go over the results or possibilities here written out as a theorem. So we'll say for a given power series, the summation as n goes from 0 to infinity of c sub n times the quantity x minus a to the nth power, there are three possibilities. First, the series converges only for x equals a. So this means where it's centered at. Two, the series converges for all x. And then three, there is a positive number r called the radius of convergence, such that this series converges for the absolute value of x minus a is less than r, and diverges when, or if the absolute value of x minus a is greater than r. We don't know about the absolute value of x minus a is equal to r, so we must check. So we're going to take a look at about 3 examples here. Let's find the radius and interval of convergence for the power series that'll be given here. This time we'll have the summation as n goes from 1 to infinity of x minus 6 to the nth power over n squared. So right now, if we notice this quantity x minus 6, this means this is centered at 6. So for sure this is going to converge at 6, but we're still going to use the ratio test to find out a little bit more about this. So this is where we want to write out a sub n plus 1. This becomes x minus 6 to the n plus 1 over the quantity n plus 1 squared. And then a sub n is just equal to what we were given. So then we'll take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. This becomes a limit as n goes to infinity. And again, I'll just take the first a sub n plus 1 and multiply by the reciprocal of a sub n. So we get x minus 6 to the n plus 1 over quantity n plus 1 squared times n squared over x minus 6, that quantity to the nth power. I'm going to rearrange some things here. So anything that has the x, I'll still leave that in absolute value, but we'll just get absolute value of x minus 6, because if we subtract our exponents, I'll just be left to the first. And then the second part, we know n's positive, so we're just going to write this as n over n plus 1 squared. And n over n plus 1 squared, as n goes to infinity, this is just going to go to 1, because this will become 1 over 1 plus 1 over n. So this will just go to 1. So we're just left with absolute value of x minus 6. So if we go back to the results with the ratio test, we would say, so this converges if the absolute value of x minus 6 is less than 1. And just go back to the description of the ratio test. And then we would see this. So what this means is if I were to rewrite this, that x minus 6 is between -1 and 1. And if I add 6 to both sides, I'll get x is between 5 and 7. And we'll come back to interpret this. But let's check the endpoints, 5 and 7. So when x equals 5, the summation as n goes from 1 to infinity. So we had x minus 6. This becomes 5 minus 6 to the nth power over n squared. It becomes a summation from 1 to infinity of -1 to the nth power over n squared. And then this would be convergent by the alternating series test. The terms go to 0 as n keeps increasing, and the series is decreasing. Let's check x equals 7. We would just get 1 over n squared. And this is convergent because this is a p-series. And p is greater than 1 here. So we can include the 5 and the 7 to help us out. So we say the interval of convergence is from 5 to 7 inclusive. And the radius of convergence, when we go back up here to the absolute value of x minus a was less than 1, that means our radius of convergence is 1. But it's centered at 6. So again, we can include both endpoints because the series was convergent at both endpoints. And just to get an idea, if we say we're centered at 6, if we go over to 7, over to 5, that means our radius would just be 1 on either side. Let's take a look at another example. Same directions here. Let's find the radius and interval of convergence of this series. Summation as n goes from 1 to infinity of x to the nth power over n factorial. So if you notice where x is, there's no quantity here, so that means we're centered at 0. And we'll use the ratio test. So we'll let a sub n plus 1 become the quantity of x to the n plus 1. Over the quantity n plus 1 factorial, and a sub n is just going to equal x to the nth power over n factorial. So our limit as n approaches infinity of a sub n plus 1 over a sub n in absolute values becomes limit as n goes to infinity. Again, we'll take our a sub n plus 1 times a reciprocal here, so n factorial over x to the nth power. And again, we'll kind of switch this around. We'll just get x left, absolute value of x. And then this will become just 1 over n plus 1. Because remember, this is n plus 1 times n factorial. So we just get 1 over n plus 1. So as n goes to infinity, this is going to become 0. As our denominator keeps getting larger and larger. So then this whole thing will just become 0, which is always less than 1. Because remember, x is fixed. So we could even think of this as x over n plus 1 will go to 0 as n goes to infinity. So this series converges for any x. Hence the radius of convergence. So when this happens, we say the radius of convergence is infinity. And the interval of convergence is all real numbers, so just from negative infinity to infinity. And we'll take a look at one more example. Again, let's find the radius and interval of convergence. Of this series. The summation as n goes from 1 to infinity of x to the nth power over n times 3 to the nth. And again, this is centered at 0, so we'll use the ratio test. A sub n plus 1 becomes x to the n plus 1 over the quantity n plus 1 times 3 to the n plus 1. and a sub n is just equal to x to the nth power over n times 3 to the n. So the limit as n goes to infinity of this ratio again, we'll multiply the first a sub n plus 1 by the reciprocal of a sub n. I'm doing this carefully. We're going to be left with, we'll just leave everything inside the absolute values here. So we'll just have one more factor of x up top. We have one more, we'll actually have n up here. We'll just leave that alone. We'll have the n plus 1 down here. And then I have one more factor of 3 in our denominator as well. So again, if we were to just look only at n over n plus 1, remember that's going to go to 1 because we would have 1 over 1 plus 1 over n. So that part just goes to 1. So we're left with the absolute value of x over 3. And remember, this converges when the absolute value of x over 3 is less than 1. And we want to solve this for x. We just multiply both sides by 3. So we get the absolute value of x is less than 3. So the radius of convergence is 3. And since the absolute value of x is less than 3, to help us get our interval, this means x is between -3 and 3. And we want to test our endpoints. So when x is equal to -3, the series becomes -3 to the nth power, and then that's over n times 3 to the nth. So we can actually pull out a -1 to the nth times 3 to the n over n times 3 to the n. So we are left with -1 to the nth over n. And this converges. This is an alternating harmonic series. And let's check when x is equal to 3. And we just get 1 over n. So this diverges because it's the harmonic series. Not alternating, just the harmonic series. So we can include the -3, just not the 3. So our interval of convergence include the -3, but not the 3. So for any number between, it will converge, just not at the right end, but it will at the left endpoint.